Hello everyone. In this video, we will work with finding centroid of a thin flat plate represented by an area. The definition of centroid. The centroid, or the center of gravity of a mass, is the point at which all the mass can be considered concentrated. Before calculating the centroid in various figure and shape, moment need to be mentioned. In a linear system, moment is equal to mass times the distance. Before I continue on, I would like to mention to everyone that I have been finding a sore throat. So if I pause, take a sip of water, I will let you know. Okay, so I haven't put up videos for a while because I have been finding this sore throat right here. Alright, so let's consider this figure. The two children are sitting on a seesaw. In order for the lever to be balanced, child A will have to sit near the fulcrum. So right here is the fulcrum. Alright, so I will make a point right here to show you that it is a fulcrum. So right there, okay, I'm going to project this onto the x-axis. So if I project it onto the x-axis, you will see right here, I can try to point it down to present this point as x1. And where this child B sits, I will assign it as the x2 on the x-axis. Okay, and again, where this child A sits, I will assign this point as x1. Alright, okay, so the x bar is the point, or they call it the center of mass, right at this point at the fulcrum, represented by the x bar. So we call it the x bar. Okay, child A will have the mass of m1, child B will have the mass of m2. So let me draw this onto the graph for everyone. Okay, so I will draw this. Alright, okay. So what I'm going to do is I am going to use these formulas. Okay, moment equal to mass times the distance to show you how we can find the value for the x bar. All right, okay. So I will do it below here. So first of all, consider the distance from where the child A sits to the fulcrum is called d1. Okay, so d1 will be equal to x bar subtract x1. So d1 is equal to x bar subtract x1. Okay, so the same thing here. I have from the point the child B sits, I assign it as the x2, and from this point to the fulcrum is called the d2. So d2 will be equal to x2 subtract the value of x bar. Alright, so I will write d2 equal to x2 subtract the x bar. Okay, so we want this distance to be a positive value. So you take x bar subtract x1, and you take x2 subtract x bar. Alright, okay. Now, since according to Archimedes' laws of lever, moment is equal to mass times d times the distance. So I will say for child A, his mass m1 times d1, okay, could have to be equal to the mass of child B, which is m2 multiplied by d2. Okay, and they should be equal to each other. Okay, so since m1 times d1 is equal to m2 times D2. Okay, so this is the law of lever, so that the seesaw will be balanced. Okay, so according to Archimedes' principle, the law of lever, that's what we have to write. All right. Okay, so what I'm going to do is I will replace D1 by the value x bar minus x1, and I will replace D2 by the values of x2 subtract x bar. Okay, so now this formula will become m1 times x bar subtract x1 will be equal to m2 multiplied by x2 subtract x bar. All right, okay, so let's expand the brackets. So I'm going to expand by multiply this into the bracket. So multiply this into the bracket or distribute the term. I should have m1 x bar subtract m1 x1 equal to m2 x2 subtract m2 x bar. Okay, what I'm going to do is I will rearrange the term. Okay, rearrange the term by whatever term involving the x bar, I will move over to the left hand side of the equation, because in the end I want to isolate and I want to find x bar, right? Okay, so I will write it as m1 x bar. Okay, this term right here, I bring it over to the other side. I will have plus m2 x bar. Now m2 x2, and I bring this term here over to the other side. I should have plus m1 x1. So the next step is to factor out the x bar. Factor out x bar, I have m1 plus m2 and still equal to m2 x2 plus m1 x1. So I will divide both sides by m1 plus m2. So x bar becomes m2 times x2 plus m1 times x1. The whole thing divided by m1 plus m2. Okay, so in the end, this is the centers of mass, right? Center of mass represented by the x bar. If we project it onto the x-axis, okay, it will be equal to, okay, so this is called the sum of all moments divided by the sum of mass, of all the mass. Okay, so if we go back to the diagram, you see this, okay, the sums of all moments. So moment is defined as mass times distance, right? So then I have m2 times x2 for chi b, and I have m1 times x1 for chi a. Okay, so this is the sum of all the moments and divided by the mass of chi A plus the mass of chi B. So in this case, it's called the sum of all the mass. Okay, so this is just the 2D dimension that we are talking about, right? So in this case, we are talking about a linear function where we have just on the x-axis as the x bar. Okay, so now if I would like to project it onto an area, okay, so if I project it onto an area, then I must have the y-axis as well. Okay, so project it onto an area, onto a Cartesian plane, I will have x bar as the ordinate for the centroid, the x-axis and the y-axis. Okay, so centroid on the Cartesian plane will have to be represented by the coordinate. Okay, so in this case, x bar is called my divided by the area. My is a moment about the y-axis, where my will be equal to m1 times x1 plus m2 times x2. And this is the sum of all the moment about the y-axis, which is called my. Mx is the moment about the x-axis, which is called mx. So the sum of all the moments right here. Okay, so this is actually the area. But if we have an area that have various shapes, okay, with a various shape, we have to use the concept of integration. So my divided by area in this case, okay, so my is calculated by the integral calculated from a to b, so which is your upper and lower limit on the x-axis, with x multiplied by y2 minus y1 as integrate as a function of x. And the area, to find the area, is the integral from a to b of the upper function minus the lower function, and in terms of dx. Okay, so talking about this, I would like to mention the formulas sheet that I have prepared for everyone. So I will go to this formula sheet that I prepared for everyone, and this formula sheet represent quite a few things here. So first of all, definitely integral fundamental theorem, we already learned about that, but I want to remind everyone the area between the curves right here. Okay, so in this case, don't forget what element that you are going to use, the dx or the dy. Okay, so either you use horizontal element or the vertical element. All right, okay, so I also summarized the centroid by integration. Centroid of the thin plate represented by an area with various shape. So the formula is also right here for everyone if you want to use this as a reference to work with any practical problems that I'm going to assign for you later. Okay, so let's get back to our lesson. So this is the formulas to find the x-ordinate of the centroid, represented by the x bar. Okay, so this is, I will derive these formulas for everyone. And this is the formula to find the y-ordinate, okay, which is the mx is the moment about the x-axis divided by the area. You see the formulas for the area is given right here. All right, so it's the same. So the integral from a to b, upper function minus lower function, as dx. Dx is the horizontal, the vertical element. Okay, so to make things easier, I am using these formulas to find the y bar. For mx, it will be equal to a half integral from a to b of y2 squared minus y1 squared and dx. Okay, so dx again is our vertical elements. Okay, excuse me. So as you notice that we only work with the vertical element in this case. I am avoiding the horizontal element because it's actually very complicated if we have to use the formulas to find y bar in terms of horizontal element. It's actually very tedious. So I recommend that we are using these formulas here so we are consistent and using just the vertical element. All right. So what I'm going to do next is I'm going to ask you to examine the following graph. Okay, so this is the area of any shape that we are going to deal with. So we learned about this in previous lesson to find area between these two functions, and you are going to identify the element so that the element will touch both curves. So in this case, obviously, is the vertical element. Okay, so in this vertical element, what I'm going to ask everyone to do is vertical element represented by dx, right? So I'm going to identify some point on here for everyone. Okay, so let me zoom it out. So this is the y-axis. Excuse me. So this is the x-axis. And on here, I am going to ask everyone to remember this as dx. Okay, so this is dx. Okay, and I'm going to identify the point on here as my y2. So let me make sure that I have a straight line going through this. Okay, so this is y2, and right here I'm going to identify, project it onto the y-axis. So this should be my y1. Okay, so now the point of intersection will be your upper and your lower limit. So right here will be my A, and right here will be the B. Alright, so I would like everyone to take a look at the shaded elements in green. Okay, so this is very important for us to derive the formulas for the x bar. Okay, so I'm going to identify this as the area. So this would be my D area. So I want to identify this as the area for this particular element. Okay, so the point on here that I assign for everyone, I would like to make it as x and y2. Alright, and right here I would like to identify this as x and y1. Okay, so the point x is in fact projected down. It's just right on the x-axis, and I just want to call it x in general. Okay, so y2 is in fact your upper function. Okay, so follow my pointer right here. So this is my upper function y2, and this is my lower function y1, because don't forget that you have to put your eyes within the bounded area. Okay, so that's why I'm asking everyone to make sure that you shade the area in before we do anything else. Alright, okay, so I would like everyone to take a look at this. Okay, so from y2 to y1, I want to find the height of this d8. Okay, so the height of this d8 will be y2 minus y1. Okay, so I'm going to write it, the height equal to y2 minus y1, and the width is equal to dx. Okay, so see this dx right there? Right here is the dx. Okay, and right here is y2 minus y1. And I'm going to find the area for this. So the dA, which is the area that I define for this green part, will be the height times the width. Is that right? Okay, so the height is equal to y2 minus y1 and multiply by dx. Alright, okay, so this is very important. We will assign this as a star for this equation, and we continue with the next concept. So the next step is given the moment about the y-axis is d my will be equal to x times the dA. Okay, and I am going to integrate what I'm going to do is I'm going to substitute. Okay, you see here the dA, so let me put it in red. I will substitute what dA equal to into this equation. Okay, so make a note that I'm going to substitute the equation star into this equation. All right, okay. So if I substitute into this equation, it will become d of my will be equal to x times y2 minus y1 dx. Okay, so now I'm going to integrate both sides, because integration is an operation in calculus. So if I perform the operation on this side of the equation, I can go ahead and do the same thing on the other side. Okay, the integral of d my will be just my. So my is equal to the integral of x y2 minus y1 dx, and we are going to work with definite integral here. So from a to b, according to our diagram, that we are working with the upper and the lower limit, a and b. So now what I'm going to ask everyone is recall what I have defined here for everyone. Okay, so the x bar is the ordinate for the centroid, will be equal to the moment about the y-axis divided by the area. Okay, so what I'm going to do is I will put them all together as x equal to, since, okay, my equal divided by area equal to x bar. So what I'm going to do is I will substitute x bar equal to my. I already figured out the integration. So the integral from a to b of x multiply y2 minus y1 dx. Okay, the whole thing divided by the area. So what is the area of this entire figure? So for this entire figure, the area that we have here, so that's why I ask everyone in all your tests and your exercise, you have to shade the area in. Okay, so the upper function is y2, the lower function is y1, and the integral from a to b, y2 minus y1, and integrate by the function dx. All right, okay. So let's talk about these formulas for a moment. All right, so according to algebra, all right, okay, so you are finding the integral of x multiplied by the upper function minus the lower function, and you have to find these values and divide it by these values. So practically, you need to perform this operation, then perform the operation and divide one into the other. So I don't want everyone to think that you can just take y2, subtract y1 and cancel this out. It doesn't work that way. All right, okay. So this is the operation that you have to take x multiplied by the upper function minus the lower function, and then you integrate this using definite integral or the fundamental theorem of calculus to calculate these values, and then you also find the area, then divide it by one into the other to find your y bar. I mean your x bar, I'm sorry. Now, so I'm a bit ahead of myself. So now I'm going to talk about y bar. All right, okay. So for y bar, all right, so y bar is a lot easier if I am going to use these formulas, which I will not derive for everyone because it's actually quite complicated. So this is the moment about the x-axis divided by the area. Giving you this formula, a half integral from a to b of y2 square subtract y1 square and integrates as a function of x. The whole thing is again the area from a to b, y2 minus y1, and the dx. Okay, so using these formulas, you will use the same vertical elements that you have already figured out in the area that you shaded. I just want to mention to everyone that this formulas, the numerators, perhaps it will be a bit tedious to calculate, but in fact it's a lot easier than using the other elements. All right, okay. So I would like to mention a bit about the example that I'm going to work with here. Okay, so actually this one should be example 1, if you can correct that for me. So this is example 1 because I only work with one example in this particular lesson. All right, so I will work with this example in the next video. Okay, in the next video I will work with this example because I only have 30 minutes for each video, and I don't want to go past the time, because with this video or this example, it will take me a while to complete. Okay, finding both x ordinate and y ordinate, we will have to do a few important steps here. But before we are going to stop the video, again, I would like to mention to everyone that we are going to shade in the area. Okay, so we shade in the area, identify the upper function and the lower function, and in this case, obviously we have to use the vertical element so that we can have the x. Okay, so the upper function in this case will be this parabola opens down. Okay, so that's why we have to shade the area to realize which one is the upper function. So my y2 will be equal to 2x subtract x squared. Okay, the negative in front of the x squared identify that this parabola opens down. So the other one, this parabola opens up, is my y1. Okay, so in this case, y1 is equal to x squared minus 4. All right, so what I'm going to do is I'm going to stop here. Okay, I will stop here, and I will continue the next video to find the coordinate of the centroid of this area for everyone using integrations. Okay, thank you.